Welcome to the first video in our series focused on strength of materials concepts. This first video introduces free body diagrams, or FBDs. We'll discuss what they are and how they're used. Free body diagrams, or FBDs, are really a visualization of the forces that are applied to something. But what does this mean? The simplest way to think of this is to ask what would happen to the object if I removed a force. If there's no change, then that force does not interact with the system of interest. For example, this box. If we remove the table, the box would fall. We can represent this as the box with forces or arrows that represent those forces of gravity and the resulting normal force instead. Look at some truss or frame systems and how the pins have to take a reaction force. For that matter, what is a reaction force? Well, a reaction force is simply a force that has to exist in order for a system to remain in equilibrium, or stationary. Let's see what happens if we remove a pin or two on these truss systems. Let's start by simplifying the truss into a line diagram with the reaction forces. In this case, we can assume there needs to be a reaction at both pins in both the X or horizontal direction and in the Y or vertical direction. What would happen if we removed the vertical reaction from the bottom pin? Like this. Well, the system would fall. Let's go back to the initial system. What if we remove that pin outright? So we remove both the horizontal and vertical reactions. Well, in that case, the whole system rotates or falls. This means that all of these reaction forces are needed to represent the truss and ensure it remains in equilibrium or stationary, and that it behaves as we would expect it to. We can look at a slightly more complicated system that has multiple ligaments and pin locations. As before, we can represent this as a set of lines with reaction forces at the pins. This time, let's see what happens if we remove one of the rods that holds the system together. Like so. Here too, the rest of the system will rotate and not stay in its original position. This tells us that each of the rods in the truss carries some of the load, not just the pins, and they are required to make the system act as we would expect. Let's go ahead and take this truss system and break it apart at every joint and see how we can represent this as a bunch of free body diagrams. And at every point that the components come together, there has to be a reaction force. We can apply both horizontal and vertical components as we did before, or we could simplify this into a resultant force that is aligned with the rod. And we can do this for all of the systems. If we do this, we can see that we have what we call a two-force member, that it has two arrows representing the load. These arrows tell us the internal force the system sees, and the direction tells us if the component is in tension or compression. The bottom rod can experience an additional force in the middle that will lead to a more complex loading scheme and will be a focus of future videos. If this video was helpful to you, please consider leaving a comment, clicking the like button, and subscribing to the channel. In our next video, we'll be learning how internal forces result in stresses and strains in the material. See you in the next video.